Hi, my name is Bob Greenyer, and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome this new tax year, the 6th of April 2025. My name is Bob Greenyer. If you didn't catch that, this is Maverick. What am I going to be talking about today? Well, if you haven't seen it, I recommend you go and have a look at it on remoteview.icu or on the @MFMP YouTube channel. I shared the water treatment faucet attachment of one Pavel Osmera. So I suggest you go and have a look at that. You can see it in all its 4K glory, which I can't stream to you here. So can you hear me? It would be good if you could let me know. Hello, Artifact. Joseph Collar, Tammy. Athena Max, Simon Flynn. Martin Kemp, Pyro Pedals, what a great name. Watkins International DIY Projects with Chauxis. EBB. Yes, we have people from all over said globe. Whoa, sky's not the limit as well as in the house. Astros Sentient Code, very good. And Crypto Alchemist, thank you for joining us. Kelly McRaven. And Citizen Journalists, it's wonderful to have you here. And Contraption. Overwhelmed Games, what a good group we have here. Well, I've had an interesting week, and I will share a couple of things. I've got an early start tomorrow, and I've got quite a week ahead of me, so it's not going to be that long. You might be pleased to hear, for a change. But I wanted to discuss the subject of Maverick. Back in late 2016, early 2017, I was invited by Cambridge University to speak at a Maverick conference as a researcher in Lena, I guess. And then I had all kinds of things arranged for me, and that I arranged, experiments that I did on the Aura project of one Thomas Jezierdynek, aka Me356. And also I was to travel to India to present at the Mumbai Technical College, where I met Suhas Ralkar. And that started a whole journey on the Echo reactor, which was my first introduction to ultrasonics. And also how sound plays a huge role in this whole field. I was lucky enough also in that year to be sent the first reactor by one Neil Crichton Gold, sadly lost. Also went under the secret name of Lion. This has been quite a few cases where we've had people that have done significant contributions to our collective research, but for the most part of their time, they've wanted to remain anonymous. In fact, Lion, Neil Crichton Gold, took his anonymity to his grave, but his wife gave me permission to share his name posthumously. So we must thank them for their effort. I was also invited to write an X Prize. I was offered $50,000 in that year to write an X Prize for Lena. I was offered $6,000 effectively a week and three flights to California, and I turned it down. I turned it down because I'd already agreed to do these open experiments. Moreover, I didn't really agree with the way X Prize gets to see all of the information before they choose a prize. That there's all kinds of risks there. So it was about keeping your word and some moral objections to the process, I guess. Been a bane of my life, but it is the way I'm made. I also was very open about how I felt the technology relied on the work of one Kenneth Radford Shoulders and the study by him of one John Hutchison. And I have here someone who knows John very well. She's just sitting over there. She's called Yin. Yin Gazda. Hello, Yin.
Yeah. Hello, everyone. Hi. Good to be here.
So Yin is monitoring my monitoring here. And I spoke about how this technology was used in what I call the event. And post publishing what I called at the time Red Pill, I was then subsequently asked to withdraw from my planned invitation to go and speak at Cambridge College at the Maverick conference. So there's a certain level of Maverick that people can take, and there's a certain level of Maverick that people can't take. And that's that story. Well, I had a very interesting experience last week, and I worked with Ryan Hunt and Matthew Villat principally in the early part of the project to replicate, as you know, for those that have been here quite a while, the work of Professor Francesco Celani. And he worked at the Italian National Nuclear Research Facility at Frascati, and he did his what was called the Celani wire. And that was a very rewarding experience, and if it wasn't for potentially, and it would seem, on the 12th of the 12th of the 12th, 12/12/12, California times, launching an experiment that 2 days later I would be able to present in Rome, producing 12.5% excess heat, I would not be where I am today, most likely. That work being replicated was the first major replication of a technology outside of those replications of Pons and Fleischmann in the early years, and the work of Toyota and Mitsubishi replicating each other. It was the first replication by a really independent party, and that later was represented to the European Union and was part of the process of convincing them to support European companies and organizations to the tune of about 11.5 million euros. We did apply. We applied with Alexander Parkhomov and some other parties, but we were not successful. And then the projects launched. Well, it was to my surprise that one of the venues that received the money, I think something around of the order of about €1 million, was the old university. I actually got an entrance to this university. I got an entrance to the Dayton Electronics course. It was their top electronics course at London Imperial College in London. And I went for their open day up there, and I was in one of their buildings in central London, and they had this big speech about how wonderful they were at doing this whatever research. I think it was something to do with LCDs or something. Anyway, they had this wonderful lecture by this man in this lab. And at the end of the lecture, they said, "Are there any questions?" And I put up my hand and said, very keen. I said, "Yes. Can we open the windows in this building?" And they said, "No, it's air conditioned." I said, "Right, I'm not coming here." So I like my fresh air, let's put it like that. So that was me not going to London Imperial. But in 2014, I visited them. And of course, we'd had our successes, I think 2013 or 2014, after we'd replicated Francesco Celani. And I wanted to kind of get them up to speed and see if they would be interested in it. And essentially, I was humoured for a little while and then laughed out of the building. So it was interesting that out of the open effort of the project to which I was a contributor, they received €1 million later on. In 2014 or 15, I gave a presentation up the road here at the Brno University of Technology. It was very well received. I didn't hear anything back other than the thanks that I got when I was there. And 3 or so years later, 4 years later, whenever it was, they received nearly €750,000 for this research. So that's the way the cookie crumbles. And what I wanted to share with you is the projects that were there, And I will find them now. I have them somewhere here. I had them up earlier. At least I thought I did. Let me see if I can find this. Now, actually, a former director of the MFMP became one of the lead researchers because of his experience in the Clean HME project, which was one of the 2 European projects. And this was principally led by Konrad Czerski at the Szczecin University in Poland, where I presented at ICCF 25. And this is their website, the Clean HME project. And you can see the people involved here. You have University of Szczecin, Institute for Solid State Nuclear Physics, Broadband Energy Technologies. This is out of Finland. This is a good friend of mine that runs this. Akademia Morska, W. Szczecin. I'm not very good with Polish, you might tell. might tell. Institute Joseph Stefan, Futuron, Politecnico di Torino, Polytechnic di Torino, Institute Nazionale di Frescati Nucleare. That's because Francesco Celani was involved in this. Uppsala University, you might have heard their name mentioned a number of times with the research with Andrea Rossi, Lugano report and other reports. Vegatech, University degli Studi di Siena. This is where Francesco Piantelli was to a degree. Centre National de Recherche Scientifique, Sart von Rohr, LIFCO, LACOCO, and Lakehead University, which I think you'll find out that's actually in America. So those are the people there. And if you go to the news here, downloads, you can go to scientific publications and you can find out, like this particle image that they have here. And Konrad Czerski up here, 2022, deuteron nuclear reactions, extremely low energies. This is in Physical Review C. You have electron screening in palladium, gypsum and quartz specimens in compression failure, fractal emissions and related stoichiometric balances. So this is an investigation by Carpentieri. We talked about Alberto Carpentieri's work in the past. This electron screening is very much a brainchild of Konrad Czerski, hence why he's leading the project. Here we have crystal lattice defects and deuterated zirconium in presence of O and C impurities. And I do know that Matthew Villatte was involved with that. So there we go. That's a former director of the Martin Fleischmann Memorial Project, a founding director, a good friend. More Alberto Carpentieri here. More Alberto Carpentieri here. Konrad Czerski. Jean-Paul Biberian, the lead author of the or rather editor of the Journal of Condensed Matter Nuclear Science here. And again, we have another one with Czerski in here. So now, I think the an excess heat experiment was this one, excess heat in nanoparticles of nickel in hydrogen. Okay, so in this titanium work, Matthew Villatte was doing a lot of preparation and characterization of the zirconium and impurities and stuff. But in terms of creating any working device, I think the closest was probably Jean-Paul Biberian's work here. Thank you very much, Gary Johnson, for that £10. Very gracious of you. And you can see that Matthew Villatte worked on that as well. So you can see Matthew Villatte is here. Matthew Villatte is here. Matthew Villatte is here. So he's in. Matthew Villatte is here, and so on. So Matthew Villatte is probably across the most of the several of the major areas of the research there. So thank you to my friend and former director of the MFMP for his contribution. to this project, which has now ended. It has now ended, sadly. And there doesn't seem to be a renewal, which is even sadder. The other project here is the Hermes project. And you can see we have University of Turku, Finland, Technical University of Munich in Germany, Laboratory Electrochemistry and Physiochemistry Materials and Interface France, Central European Institute of Technology, Brno University of Technology. These very same people I was talking about, they're basically one of the leaders in this. Czech Republic, Imperial College London, as I said, United Kingdom, University of Limerick, Ireland, Aalto University, Finland. And for anyone who doesn't know, Aalto University were the people that in 2009 predicted a topological monopole. Thank you very much, Philip Power. Philip Power has been helping me proofread some of my work and his own efforts in the OCRing of the remake of Dr. Matsumoto's book. And we're going to look at a couple of pages of that in a minute. So Aalto University here, they came up with the topological monopole. And later, that was in 2009, and later in 2014, they synthesized it in a Bose-Einstein condensate in 2014. And I think one was in Nature and one was in Science, of the two. So they were involved as well. So you can see it's all European Union funded. And actually, in terms of the papers published, I think they had a slightly higher output, but then more university-based. So in 2021, you can see there was, and you'll have to look at this yourself, and I'll share the links in the blog afterwards. You have in situ detection of active sites for carbon-based bifunctional oxygen reduction and evolution catalysis. Monitoring the active sites for hydrogen evolution reaction, model carbon services, so on. High precision method to reveal active sites. A trade-off between ligand and strain effects, optimizing the oxygen reduction activity of platinum alloys. Revealing the nature of active sites on platinum gold and platinum praseodymium alloys during the oxidation reduction reaction. Structure-dependent electrical double-layer capacitances of basal plane palladium electrodes in HClO4. They're catchy, aren't they? So elucidation of structure activity relations in proton electro reduction at palladium surfaces. You can see a lot of palladium going on here. Platinum and palladium, platinum electrodes. Here we've got hydrodynamic methods in electrocatalysis, electrocatalytic sites, nanosheets of graphite, electrocatalytic centers. I don't see a lot of LENR experiments in here. I see things that are trying to characterize things that would happen in palladium. You see we've got palladium nanoparticles here. So controlling the reactivity and interactions between, I'm going to zoom in so you have a chance of reading this. Controlling the reactivity and interactions between hydrogen and palladium nanoparticles via management of the particle diameter. Neutron diffraction and discrete Fourier transform studies of oxygen defects and transport in higher order Ruddleston-Popper phase materials, catchy. Isotope effects in the electrode deposition of silver and palladium. And enhanced CO functionality on carbon papers ensures lowering nucleation delay of ALD for RU towards unprecedented alkaline Her activity. Well, unlike the screening that was achieved here in this project and the actual apparent excess heat in particularly prepared materials published by Jean-Paul Bavarian here and with Mathieu Villat on there as well. And Jacques Frouard, someone I really appreciate in the French community. I don't see anything here. Okay, so again, they have finished. Now, when I reached out to them, because I thought, well, they're just not very far up the road from me. So let's see if I can help them get started, because you don't want the disaster effectively at any point that the Google money was thrown away on. Anyway, so I was told fairly early on that the European Union had been advised by people connected with US Navy, and I was shocked and disappointed because I really thought this was a chance for independent thought in Europe. I don't have the paperwork on that, so don't hold me to it, but that's what I was told by a source I know very well and trust. Of course, there was all this talk about focusing on electron screening, and also, as you've seen from the Hermes project, a lot of focusing on palladium and it turns out deuterium. So I really wanted to help them out, and I went straight in like a bull in a china shop and tried to share my experience for free with the project that was being in part led up the road from me. It's literally just like 12 minutes away. And so one of the most important things that came out of that actually was, after about 6 months of trying, I was given an opportunity to have some scanning electron microscopy done, and one of the people on the team was given to me for a few hours or afternoon, and I was able to use their SEMs. And this was right at the start of me trying to replicate the replications of the Ultra experiment, the early Ultra experiment. And I can't even remember the date, but we're going to look at it now. I'm going to go to a typical presentation where I might have thrown this slide into. Yep, here we have it. And I'm going to drag it up here so I can zoom in. And what I'm referring to is the Ultra experiment you can see down the bottom corner here. And that is here. And you can see, and we're going to find out the date together. I'm going to remember it together. Oh God, I've got it covered up. This is the 8th, oh no, 13th of the 8th. So 13th of August, 2021. 13th of August, 2021. So what is that? That's like 4.5 years ago, something like that. 4.5 years ago. I went in, did this session, left, and I never heard another word. But you know what? That's okay, because we got this. And we got many more images from this session, and this really led us to understand that the process produces scale invariance. The Coulomb barrier is not a thing. The toroidal moment derived from, was supported by, or the importance of the toroidal moment, and this magnetohydrodynamic geometry was very much supported by this early Ultra work. But you see here this bar spiral galaxy structure. We confirmed that these structures are scale invariant, and so this is a representation of that. And we also showed heavier elements synthesized on the yin side, and on the yang side, lighter elements from the starting material. This is just one of the many images that we got that day, and it was very, very significant in the journey. So I thank the leader of the project there for putting me in contact with one of his staff and allowing me to share a bit of my experience with her that particular day. And so we got these images. So this was very valuable. And then I didn't hear another thing for 4.5 years. Until that is Thursday at about 4 o'clock in the afternoon. maybe 3 o'clock. I got a phone call. And the person on the other end said, "Hello, is that Bob?" And I said, "Yeah." I said, it's Jan. I said, well, I didn't really know which Jan because I know quite a few Jans in the Czech Republic, and I know some Jans, as you saw in the video that I shared earlier this week, in Denmark. So I know quite a few Jans. So I wasn't quite sure who I was speaking to. Anyway, he was saying, Jan, this person, Jan, said, you remember, are you still living, blah, blah, blah. And I said, yes. And he said, we're having a closing dinner for the end of the Hermes project. And we're wondering if you'd be able to come over and give us a talk. Really? Okay. All right, fine. So I carved out the time and went. This was on Thursday, so I already had the full day completely blocked out. So I said the earliest I could be there was 7:30 in the evening, and then I was working with Thursday and so on. I got a message on my phone said 45. I saw 45 at the back of the end of the message. I thought, okay, must mean he's saying come at 7:45. So I just said, yeah, okay, that's fine. And then when I was in the end of just publishing the last video on Thursday, the one where I'm speaking to the Scandinavian team about the thunderstorm generator, it turns out he actually wanted me there at 5:45 so that we could talk with their team for about 2 and a bit hours before we went to dinner. Anyway, by that, it was never going to be possible. I thought I tried to make that clear, but anyway. And so I turned up at 7:20, 10 minutes earlier than scheduled. And and I shifted the last video to 10 p.m. in the evening so I could hopefully interact with some of you guys. And I sat down, and every single person of the Hermes project was there. I'd only ever met him and the woman that had helped me do this scanning electron microscopy here. But every single person was there. And it's not really doing it justice, and you can only see part of it. And I'm going to cover up the man's face to save his modesty. But here you have it. This was the table. Okay. And there's my nose. And there was a very large group at this meeting, final meeting. And he then proceeded to apologize and apologize again and apologize and apologize and apologize again. And I thought, stop apologizing. He was finally free to talk to me because he'd been told he couldn't talk to me. Yeah, he'd been told, yeah, we weren't given any European Union funding, but we were also not allowed to be spoken to. Now I'm kind of understanding why maybe Google didn't speak to us either. I don't know. But the project was over. That was the last dinner, and so he could talk. And this is interesting because I had the same experience when I went to speak at ICCF in Italy, ICCF 22 in 2019, because the then Sidney Kimmel Institute of Nuclear Renaissance project at University of Missouri had literally just finished earlier that year. And one of the people came up to me and apologized for spreading stuff about me. Basically, they had been instructed to spread stuff. Yeah. Notice pattern? Then I had the individual telling me that they hadn't actually run a Lena experiment. At least that's the impression they gave me. They tried to, and that's not true. I think they'd run the CR39 experiment and hadn't been successful, and concluded that in their experiments it was something to do with the ultrasound damage when they were cleaning the CR39. They had prepared a lot of work on palladium deuterium, and they had essentially the team that was responsible for using the palladium and prepared materials didn't get to a point in their work where they could start an experiment. Now, when you know, the experiments that they were suggested that they should have done with with who was advising them, it is my, and I feel deeply sorry for the taxpayers of Europe. These people did their best with the hand that they were given. I turned up to the meeting with Matsumoto's book. I showed them the introduction. I showed them some of the absolutely self-evident data that we have got from both ultrasound and from plasma reactors. And they were looking at each other in shock, saying, why weren't we shared this information? Why weren't we shared this information? I'm not saying it is the case, but I feel that at least on this project, where like half of the project had Matthew Vallat involved, and I helped Matthew wherever possible. Yeah, I certainly spoke to Jack Rauer. At every single presentation I gave to Jack Rauer, he really fought for plasmatorids, plasmoids, exotic vacuum objects, and for the work of the MFMP to have at least a hearing. But I know, because I sat down at dinner with him once, he was struggling to make sure that we had a voice. He really tried to make sure we had a voice. And of course, Jean-Paul Bavarian's work in that team, and the work at Poland and the Konrad Czerski, and also my Hungarian Finnish friend, I think they did some great work. But I think the Hermes project, and if it wasn't for certain people in the other project, like Francesco Celani, they were kind of set up to fail. That is my assessment. And it hurts me so much to know that I knew that that was what was going to happen at the beginning. That's why I spent so much effort trying to pound down that door to offer myself for free to help them understand the parameter space where people had gone wrong in the past, and they were told not to speak to me. They were told not to speak to me. Of course, if they'd have been successful, then maybe they'd all have extra money. They'd all be sitting pretty for the next rest of their lives, doing stuff. So I got out some of my favorite samples, which we're going to look at today. And I said, I've got a gift for you. I said, I've got a gift for you. That gift was what I would consider is from a Maverick. And like a lot of these Mavericks, they like to be under a pseudonym. But I don't even know whether the experiment will work, but it's certainly looking encouraging. And so I gave him this. A Hitano 4,700 microfarad 50 volt electrolytic capacitor. And 2 litres of distilled water. 2 litres of distilled water. capacitor like this. Now, there's a guy called Tibby. He's been looking at my friend's work, Dr. George Eagley, and my work, and a couple of others, and he's come up with an experiment which is like the very simple Matsumoto experiment that produced this, which I think is on page 89, if I have a look at it. Page 89, I think. Here. No, 90. I'm a page out. This one here. A lead wire in potassium hydroxide 1.5 molar solution. In a Petri dish. It's not very large. It's about 50 centimeters across, the experiment. Copper bowl and 120 volts at 380 millisecond pulses to produce electronuclear collapse and electronuclear regeneration. And I said, like, this is a combination between kind of ultra, the use of aluminium in ultra, which was pioneered in the US, and the work of Matsumoto. In many respects, because it's a dielectric barrier and it's water and it's one electrode with another, it's like wire electrodischarge machining, which I had established almost certainly does the same process. It is also a dielectric barrier in a way, discharge like Ken Shoulder's Evo production, or like the work of Bogdanovich. So it's very similar. In a recent presentation, I showed that the explosion of water under the surface produces exactly the cone that this researcher Tibby, who he goes by, does. So the cost of this was $2 US. The cost of 2 liters of water was $1 US. And bearing in mind, I'm buying this new. And the cost of the aluminium foil, I don't know, another $1. So you're looking at probably $4 to get up and running, even if you're buying stuff new and you need a power supply. Often people have got enough power supplies lying around the house. If they haven't, then you can find some old dead PP3 batteries, 9-volt batteries, and gang them together in series, get your voltage up, charge it up to 30 volts, and do your experiment. Do your experiment. Okay, so you can go and look at my blog on that. And so that, for me, is a Maverick approach to science. This person, for me, was a Maverick. And we're going to see a little bit more of his work. So was John Hutchison. And John Hutchison, investigated by Ken Shoulders. And I have to thank Gene Manning for giving me these 2 original photos taken. So it's an original print here of Kenneth Radford Shoulders here, and of Kenneth Radford Shoulders with John Hutchison here. Okay? Gene Manning has just launched a Substack, so go and look for it. I'm very pleased to see that. She's an excellent writer, and I look forward to seeing what she does with her Substack, so I'd recommend you go out and get there. Yeah, I showed him some samples, and one of those samples actually was this one, which I have spoken about at great length, where this particular part of the material disappeared almost instantaneously. And we've studied the edge of this, which looks like incredible scalloped areas, the same kind of thing we see on John Hutchison fracture areas. And these structures, which helped us understand the symbol of God controls power. So we have a question from Sheffy. How is John Hutchison doing? Yin, would you like to be able to let me know?
Well, he's in very good spirits and he's getting much, much better. Thank you.
There we go. He's in very good spirits and getting much, much better. Thank you, Yin. He still has his stone in his bladder, and I guess they have to wait until everything's settled down and an appointment to maybe sort that out. Anyway, that's very, very good news. Okay, so this really here is the stuff of Maverick. It's looking at the research and seeing a potential avenue forward. Seeing a potential avenue forward. Now, I have read a lot of research, and I know for a fact that people in the Lena field, for the large part, don't seem to bother. They just do not bother to look at other researchers by their colleagues. I know this because someone will give a presentation, and then I'll say, thank you for your presentation, which obviously they're good people and they do good presentations. And so I say, thank you for a good presentation. But then they are completely unaware of things that have already demonstrated the effect, or they've demonstrated the observation, or they've demonstrated a corollary to their argument, or whatever. And it always surprises me. And I am trying my best to read what I can. But what I have learned from going through the Matsumoto archives is that Dr. Takaaki Matsumoto took it to a whole next level. This guy right here, Dr. Takaaki Matsumoto, he printed every single paper from the conferences, every single one. And he noted and underlined, and you can see that he's reading through all of the documents. He's reading where there might have been an insight, where there might have been an error in understanding, and so forth. The attention to detail of this man is extraordinary. Corky says, hi, Yin. Hi, Yin, from Corky.
I just answered Corky.
Oh, she's answering you in text. She's actually watching over there at the same time. There we go. All right. So, yeah, he read everything. So I just want to, I did a short video as an update to the remaking, and I'm really rather enjoying it now. I have to say that I could not have rebuilt this book any time before December of last year. Not just because I didn't have the materials to uprate the graphics, and I hadn't helped Jordan come over and help me to get the materials scanned. Thank you, Jordan, and his wife. And I just didn't have the skills to rebuild these papers in a way that would respect Dr. Matsumoto's attention to detail. And Wayne had done some really brilliant work on layout and OCRing and so forth, but he had hit his limit on what was possible. And I have to say, this is one way that Grok AI helped. I was able to learn using Grok as a kind of like sort of expert. And so over the last 3 or 4 weeks, I've been able to get to a level where I can actually improve on the original latex that must have been used to create the original papers in the book. And it's been quite a satisfying exercise, I have to say. So on the downside, that means you might actually get some papers from me in the future. And so I was able to say, like, you know, this really highly complex equation, how can I make this? And it would have an attempt. It would get a bunch of stuff wrong. I would be able to work out kind of where it's doing things in the code it's using to do it. I would try and fix what I can. I'd see what it produced. Then I'd give it back and I'd say, look, you got this, that, and the other wrong. And after about 40 minutes, I'd managed to get something that was a very good version of what we see in the original paper. And so it's been really, really useful for that. So the membership to allow certain things to be possible on X gave you access to Grok, and because of that, it is now possible for me to do this work. So it came at a good time, let's put it like that. So I'm just going to run through the comment that I made with respect to there was this paper that was put out in January that I was sent on the 30th of January by Alexander Parkhomov about the fact that these new Israeli scientists who are geologists, they had decided that probably the Earth's elemental makeup, at least in the crust, is synthesized via Lena or some similar process. And they quoted Parkhomov's work and so forth. So that's great because that's what I believe. And so I'm going to pull up a couple of papers by Matsumoto here. And I think it's going to be dawn on you just what a genius this guy was. So if you just give me a second here. I don't want that. I want this. Okay, so I want... And honestly, in the original book and the remake, some things, because of the quality of the images, and I understand why the images were not that good quality sometimes, what he was doing is he was taking a microscope a photograph using a camera attached to a microscope objective to look at a radiographic plate, let's say. He was then he was developing that negative, he was then printing that print to about, a small 4x3 print. He would then arrange that on the paper because back in 1989 he didn't have, or 1990, he didn't have access to, desktop publishing that you would have today. And then he would take a photo of that, and that photo would then be scanned, and that scan would then go into the book and be printed. So you've got generation, 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 generation. What we are able to do is to go to the original negative and scan that directly, or the first print that he used and scan that at high resolution, but also high bit depth. Because the scanning technology back then was typically 8 bits. So we can scan these things at 16-bit and we can pull out more data. And so it's really rather remarkable how, to some degree, you can forgive people's inability to understand what he was trying to get at. But because of the quality of some of the images, it's unforgivable in some other cases, but yes, they just don't pay attention. Okay, so let's get these in order. So that would be there and here. Now, before we move on to that, I just want to talk about the video, and if you haven't seen it, go and see it. But I hope we can work out something with Pavel so that he can be part of the Evo, H2 Evo, part of the Evo Labs project. But here is one of the tap attachments that Pavelo Smira made. Okay, and it has a Venturi and a Vortex system in here. It sucks air in through the lower pressure made, and that mixes air into the system. Well, we all know where the chi is stored, according to my hypothesis. So that's not his hypothesis, that's my hypothesis. So I think it would be good. And then it goes through a bunch of neodymium magnets that are aligned in this cap here, and you get a nice laminar flow coming out of the end there. So that is his little device. He has some other variations in here. One that's got a bit of a breakdown of it. And this is the sort of thing that comes out of a Maverick mind. And before we go on to Matsumoto's genius, I'm actually going to show you a paper which I will also publish along at remote view. So you can actually see the neodymium magnet, and we've got a red spot on here, so that should give you an idea of which pole should be there. So I've got a bunch of these to try out. Okay, and it might be interesting to use these in ultra experiments to see if they seem to accelerate the process or not. So I'm just going to bring up Pavel Ismira's paper first before we go into Matsumoto's utter genius and maverick nature. So we go here, and so for those that need to reach out to him, the details are on the page. It will actually, I won't share them in the video, but you can go to the blog. This paper is called Revitalized Water, Magnetically Treated Water, and he talks about abstract. A new model of atoms and molecules was proposed. It was revealed that there must be two types, A and B, of atoms that differ in direction of rotation in individual, blah, blah, blah. So you can go and read this in your own time, but he has this toroidal model of a proton and a toroidal model of electron, and how this allows the bonding together and neutrons and so forth, the different elements in the periodic table. In terms of a structured model, this is a bit like the structured atomic model, except for it includes a toroidal structure, which actually explains how the structure fits together in a simple logical way. So he's saying that essentially the basic substructures of atomic nuclei, the left is the these kind of nuclei, and then ring structure. There's a sphere, and this is the classical model. This is his new model, the structure of atomic nuclei, and so on. And before I go there, I need to give credit to someone who actually first introduced me to Pavel Ismira. I just wanted to get that on the record. So he was a German, and so basically after I had found the 3D structures in Henk Uren's Vega experiment, and after I had sent all that in my model to the Russians and got back the Zverblis paper and translated that, and that led me to Nevesky, and then that led me to Dubovik and the toroidal moment. This guy, Raoul Sebastian John, reached out to me and said, oh, there's another guy that's got a toroidal model. And loads of people sent me toroidal models. But the interesting thing about Pavel's work, and this is why I believe he's a real maverick, and bearing in mind he was a university lecturer at the Brno Technical University in informatics. He wasn't a physicist. This makes him even better in my mind. And so he has this nuclei, and you can remember this nuclei looks very much like you saw on that Mexican mural in the atomic age. And this is the structure as he sees it. The planetary system in the standard model, and his is this, where your proton and neutron and electron all have a magnetic negative and positive, magnetic negative and positive, and so forth. So they're all got some magnetic influence, and that this leads to an electric attraction and overall repulsion system that allows the electron to levitate, for instance, next to a structure. So what you're actually looking at here is a deuteron, or a monoatomic deuterium. So you've got a proton and a proton and a neutron and an electron. Maybe the proton is the red thing here. Okay, so they're connected through magnetically. I saw a video on a podcast where there was this NASA scientist, and he was talking about how all these things actually connect together magnetically. There was some other guy talking on there that I didn't really understand what he was going on about, to be honest. He's some actor, but that's okay. Maybe he's also a maverick that has a very important thing that he's going to share with everyone at some point, but I didn't really get anything from him at that time. But the guy who worked at NASA was saying, you know, they're not points, they have these magnetic interactions, and it's all magnetic. So and then there's this string theory which is obvious nonsense because it requires 10 dimensions and is no self-organization. And he's talking, and this is totally in alignment with my view. You have dark energy, which is just the sort of sea of vibration. And then out of that emerges solitons. And he doesn't talk about these as fundamental or what they call elementary LC dipoles, but this is what I see, the elementary LC dipoles, the relic neutrino or background neutrino that emerge out of that, and that these moving, or the energy moving across them, is the radiation, and that the fractal ring vortex theory here, he says 4 dimensions of self-organization. Well, it definitely needs 3, and 4, you've got a closed structure. And so he actually has a model here of everything up to cadmium. I think he goes further than that. He shows here the you know, how they all connect together. It's repulsion and attraction. You see magnetic fields here are all these purple structures. And then you've got electric fields going on. Okay. And so it's really wonderful. So you'll be able to look at this paper, and I suggest you go to Pavel Esmira's site and have a look at his other work. And so he actually suggested, in fact, maybe I can go and look at the key. He actually builds these 3D printable models to model the elements in the periodic table. But here goes topological hexagonal model of water. Here we go. And then cell membrane, large clusters of water. So he's talking about how water plays a role. And this is the water unit that we showed earlier today, and it's really rather expensive. It's like, I don't know, 708 euros. Okay, 708 euros. He's looking to produce these and sell these units here for about 1/10 of that. Okay. So here's some of his versions of the what he calls magnetic water. Yeah, 63 euros he's going to target here. Okay. And then it comes down to his actual model of the electron. So the electron has radius r, e, and spin s. Me is the mass of the electron. Ve is the circumferential velocity of the electron in ring. And he worked with a 3D modeler who came up with this, some of these models. And this is from one of his early papers. And so it turns out that he came up with this fractal toroidal model of an electron in 2009, but from his mind, rather than from seeing something in 3D. So you have these topological transformations with the vortex pair, and it makes more vortex pairs, and you end up with a ring structure and so forth. And I think I will, if he doesn't show it, I will pull it up. So he's got various inventions in here that he's done. These vortex generators. It's a simple 3D printable attachment that you can put onto a water bottle, and as you pour it out, it produces a vortex and goes through a magnet to treat water coming out of drinking bottles, like the one I'm drinking here, but just a bigger version. So you can actually treat the water from even drinking bottles. So he's got all this logic in here and the equations for why he believes that this will work. Right, so I'm going to actually go and find his paper, because I want to give him full credit for thinking about this structure of the electron from a mathematical point of view, just conceptualizing in his head. And this is really what you have to do, I believe, to be what I would class as a maverick, to break new ground. What seemed to be tragic to see is how the people at the project, the European project, were led to do something. I don't know whether it was just so that the people that originated those experiments could feel, vindicated, and someone else is paying for it because they can't pay for it, or or to literally say, oh, these people were given 5.5 million and look at them, they're all at big universities and stuff and they can't do it. And we all know that you can replicate palladium deuterium, and that's been done. If you get a load of people that have no experience in this, then, and it's so lamentable. Okay, just give me a second. I'm going to find one of these, the paper that I'm looking for. Okay. So you can do this along with me, Pavel Osmira. So you just type in Pavel Osmira. It's the first link that comes up. This is the chap you saw in the video we shared earlier. This wonderful levitating fractal geometry. He actually does this as a coil. Okay, so if you go to publications, and he calls it Vortex fractal ring theory. Yay! We agree with that. And we go down to here. 2009 Vortex ring fractal structure of atom and molecule. So this is from 2009. And what do we have here? So he's starting to talk. You can see the genesis of the images that you just saw in his latest work, and how he's doing his calculations here and working out. And here we go. This is his 2009 3D ring within ring within ring within ring. So you've got the big wheel here, which is your N level. He calls it 0 electron. And then you've got your sub-electron here, which is your -1 electron. And then you've got your sub-sub-electron here, which is your -2 electrons. So that's a wheel within this wheel within this wheel. So he has the wheel within wheel within wheel. Then he has the -3 electron. And then he has the -4 electron. So he's showing how this goes down and down and down. And this is going to be very, very important for my presentation at the Tesla Tech conference in August. It's going to be very, very important for people to understand this kind of fractal model for my Tesla Tech presentation in August in the US. Vortex fractal ring structure of the electron. And he conceptualized this in his head. In his head. That's what I call Maverick. That's what I call genius. He has these things where you have electric rays going out and you have these magnetic lines threading through. At no point does he discuss the toroidal moment. To be fair, I believe that the original wheel within wheel within wheel ad infinitum structure was connected together magnetically. So I'm in line with what he was thinking. But anyway, I think it's the toroidal moment when it gets beyond the third order structure. So there we go. This is from 2009. Okay. And then you can see he's already thinking about his 3D models here and so forth here. Conclusions. It seems that gravitation lines from graviton fibers are in the same axis as levitating electrons. Graviton lines repel each other and due to two bodies are attracted. The gravitation lines are braids which are created from graviton fibers. Anyway, you can go and read this in there. Thank you very much, my channel. Yeah, I see big fake money pays for investigations to tie up researchers in a frame that inevitably leads to negative results. Scuttle happens all the time. Yep, I think that's about the size of it. The annoying thing is that even before they'd had their inaugural meeting, I could see what was going down. I managed to get an audience after really trying. I got those images onto the SEM. Seminal images, in my view, for the story that we've been telling. So great thanks to them for doing that. But then there was silence. And then I kind of found out a period of time later why that silence was likely to occur. And I had the absolute cast iron truth of the situation on Thursday last week. Right, so Yeah, Stephen B. Hall says, "Yay, I'm also a person who thinks gravity is tension by connecting tubes." Yes, quite likely. Right. So I'm going to go back to the work of Matsumoto, which I think is going to be key today. So this first paper, so I'll just reiterate what I said the other day. This is reference 6 in his book, but it's the first paper he chooses to put in his book, but it's his first paper in fusion technology. And you can see here it was received August 14th, 1989, so less than 5 months after Martin Fleischmann and Stanley Pons announced. And the conclusion in here, now you don't necessarily have to agree with his NATO model, although it does have a certain level of genius in its own right. It's this. His conclusion is so amazing. If the extremely high concentrations of deuterons are obtained, 12C, 14 nitrogen, and 16 oxygen can be produced by a single reaction of many body fusions. Those isotopes are stable and important constituents of the Earth. The NATO model suggests some modifications in the theory for the birth of the Earth, as well as the feasibility of the production of useful elements such as rare metals. Rare metals. Now, you could argue that scandium is a rare metal, lighter than iron. So could he be referring to that? No, I think he was hedging his bets here by not rocking the boat too much. So this is basically suggesting that we need to rethink the formation of the crust of the Earth. This is less than 5 months after Martin Fleischmann and Stanley Pons announced. Incredible. But it goes on. In the next paper, he cites work done again with, I think, palladium deuterium. No, it's ordinary water. So the paper is called Cold Fusion Observed with Ordinary Water. Again, received November the 13th, 1989. So he completed this work long before November the 13th, 1989, and it was accepted for publication in January 1990. Okay, it was actually published in May 1990 in Fusion Technology. Okay, and what you're looking at here, all these, this is my work in latex, which I'm quite happy with. Yeah, the experiment is here. So he had a 50 millimeter diameter times 50 millimeter long palladium cathode rod. It was surrounded by a 0.5 millimeter helical platinum wire. So this is the sort of thing you would have wanted the Hermes project to do. And they, with all of the different universities involved, didn't do a palladium platinum experiment in 5 years. And this guy was already publishing within 6 months, right? Like one guy publishing within 6 months, and placed in ordinary water. He didn't even have deuterium with 3% sodium chloride. The palladium rod was maintained in a vacuum at 800 degrees C for more than 10 hours to discharge the contained gas. So what this is basically the degassing process of palladium. Palladium likes to suck up gas, and once it's in there, it doesn't like to get out. So you have to heat it up. Palladium is high melting point element, and so you have to heat it up quite a lot, get those crystals to open up and shake around, let that gas out in a vacuum. So that's how he did it. And then he electrolyzed it. So the whole description of what he did is within that. That's all you need to read. That's all you need to read. And then he used a germanium lithium dope detector, and it was located beside a 50 millimeter diameter electrolysis cell. Now, we have photographs of these experiments now, not just these detailed descriptions. Both the detector and cell were shielded from natural background by blocks. These are lead blocks, effective thickness 15 centimeters. The energy calibration for the system was made measuring gamma rays from standard sources of 152 europium and 137 cesium. The background was measured when electrolysis cell was far from the detector and was repeated many times. So this guy was an expert in radiation. Now, they did analysis on a 4,096 channels, 1,024 channels, and 256 channels. And on the higher channels, where they're looking up to high up to maybe 3 mega electron volts. They're just seeing between the water experiment and background the same peaks appearing, and it's just shifting more counts without any shape changing. And there's the positron and electron annihilation line. These are all from background radiation, and all you're seeing is the difference between here and here is the time of accumulation. So there's no signal in these upper energy bands. When they're looking at 1024, so what they've done is they've scrunched down so that they're looking at this part of the frequency analysis. You can see the positron electron annihilation there. And again, over this area, we don't see any change other than for the accumulation over a greater time over the background. Okay? But when you look at this line, which is up to 256, and this is 128. So around here, we're talking about, this is about 150 kilo electron volts. So this is like about 130 kilo electron volts. Here is our background. Here is our 11-day signal, and we can already see a reasonable departure here in terms of accumulation. There's this clear bump here. Add another 4 days, and we're getting a very significant bump. This is a change in curvature of this overall structure. And moreover, this is one line, but this starts to get steeper and steeper. So there's a very interesting curve here. And you know what? We saw the same thing in GS 5.2. We saw the same thing, I believe, in GS 5.2. Hold with me. I'm going to pull up that data. If I can find it. So, if you remember, this experiment was born out of combining the understanding we learnt in January 2015 from Professor Francesco Piantelli and the work of our Celani replication and the claims that were made public by Andrea Rossi. Principally, this is Piantelli applied to Andrea Rossi's nickel plus lithium, aluminium hydride, and lithium. At this point, we hadn't realized the importance of separating the lithium aluminium hydride from the nickel, which became clear to Alexander Parkhomov shortly or around about the same time. Okay, and in this experiment, we found, there was this claim by Rossi that he had observed gamma radiation below 300 kilo electron volts. Okay, and I was suggesting, based on our data, we were seeing below 100 or around about 100 kilo electron volts. This was the signal. Trace 4, trace 5, trace 6, boom. So you can see everything is normalized to background. And then as we move forward, okay, so we're going to start again, 21, 22, 23, 24, 1, 2, 3, 4, 5, 6, 7, boom, there we go, 8, boom, and then 9, and then 10, somewhere around there. Okay, so this was when we took our reactor on our thermocouples over 1050 degrees, and certain things happen with lithium and at this temperature. Okay, and then we saw excess heat. It would apparently seem at the far end of this scale once this process had gone through. This dead time here measurement on spectrum 7 and 9 and 10 here is extremely large. And here you can see traces 7 and trace 8, and then this is the average of all the rest of them. Okay, so there was around about 90 up to a 90 or so, a 80 keV. There was this rise here. We can't see below this level because of the beryllium window on the scintillator on the detection device. So we can't see below this, but you can imagine this would go up radically. There is no characteristic X-rays here. No characteristic X-rays here, which means it must be something that is blowing up and releasing either electrons or photons at a incredibly smooth rate of emission. And what it's saying to you is that this is not radiation that came from... Good night, Gordon. This is not radiation that came from the reactor itself in terms of an X-ray that then went through the rest of the materials, because if it was, then we would see potentially characteristic X-rays emitted from the materials it went through. I believe that this was a neutral structure that came out of the reactor, went into the scintillator, got trapped there, blew up, and emitted a range of photonic and or electron energies that led to photonic scintillations, that led to this beautifully smooth array of emissions. Okay? So this was deeply, deeply analysed by Bob Higgins, and we must thank him for his work. And he produced this paper, which I'll share you in a second. I'm just going to let this run round. So this is, I think, the minus the background. So this is minus the background. So you're going to see the signal appear out of the bottom floor noise. This is a logarithmic scale. 2, 3, 4, 5, 6, 7. Boom! That is a signal. 8 is a signal. 10 is a signal. Okay. So I'm going to go and look at this. You can see this all on our historical site. So essential here, there was a significant gamma outburst in GS 5.2 whose broadband high energy spectrum is not only explainable by known chemistry and physics, but may also be not explainable by many of the present theories of Lena. Okay, and at that time, back in early 2016, I didn't know that this could be an exotic vacuum object blowing up. It couldn't be an exotic vacuum object blowing up, right? Now, to give you an idea, if we go back here, and we've got the timeline here of the experiment, 7 occurred. This is where 7 periods started. So it's a fairly long period, but it's actually from the 2nd of the 2nd, so the 2nd of February 2016 at 3 a.m. to 1500, a little over 1500. So this actually is only 12 hours of exposure. And Matsumoto's experiment was running for up to 15 days. 15 days. So let's go back to the data and we'll see some comments by, and you can see the experiment here. There we go. There is the scintillator head. These are our lead, low activity lead bricks that my colleague Alan Goldwater has. Okay. There's the overall heat treatment, the overall experiment. You can go and get this data. So we're actually talking between 7 and 8 here. So you can see how long the experiment was. It's much longer than the window that we're talking about here. And so here, this is the calibrated background spectrum. So you can see an X-ray peak here and 40 potassium X-ray peak here. That was the calibration. You can see this is the calibrated background noise. So there's almost no signals. This is like 30 counts. It's basically nothing. That is the floor noise. Here is the peak on signal 7. The peak on signal 7. It says here, now with the processing explained, let's have a closer look at spectrum 7. Copied here for convenience. As figure 6, but it is exactly the same as figure 1. So have a look at the note in the center. This is the note in the center. So the total background counts of all counts across all energy levels in background over 1,460 seconds would be 54,777. The total signal counts in the same time frame would be 1,460 seconds. This is 298,045. That's 5.44 times the number of counts in this period for a normalized period of background radiation. It says that the ratio of counts in the signal to the counts in the background is 5.44. That is a lot. That ratio is not the signal to noise ratio in the measurement because the background is not all noise. Much of it is deterministic from actual radiation. The signal to noise ratio in the total signal count will require more detailed noise analysis, but is probably more than 50. The signal to noise ratio here is 50. And bearing in mind, as we know from exotic vacuum objects, the majority of them are low energy. Low energy. So this is going asymptotically up. So if we could see lower energy emissions, it would literally, it would be a ridiculous amount of counts higher than background. Here in calibration 8, you can see that there is a signal, but it's much, much smaller. But it's definitely here. And do you know where it goes up to? It goes up to about 100 keV. And here in the next one in spectrum 9, there's basically no signal and noise. In 10, there's a little bit of return of signal, but the signal is so much smaller. But again, it goes up to about 100 keV. Okay. Why am I showing you all this? I am showing you all this because look at what Matsumoto had established within about 6 or 7 months. He had established this. On the other hand, the enhancement in low energy region is clear. Figure 3 shows a further expansion of the lowest energy region. Data obtained at 11 days are also shown. The enhancement ranges up to 130 keV. 130 keV. What I'm saying to you there is that even before the end of 1989, Dr. Takaaki Matsumoto, in a light water system, bearing in mind we were using lithium aluminium hydride and our group 10 metal was nickel rather than his group 10 metal, which was palladium. He had observed, in my view, the same signal we observed in 2016. The same signal. Why do I say that? Well, our pulse came over 12 hours, right? His accumulation here is over 15 days. The signal is mostly skewed at this end of the signal, right? Regardless of what it is. So if this here is 130 keV, then this would be 100 keV. So his peak contribution is here. But I do believe that that line is steeper than here. In fact, there's no line here, right? And could you detect a little bit of accumulation over here? Has that shifted a bit? Maybe. I don't know. It's not clear. But I think he saw the same thing. I think he saw the same thing. So I believe because we are not seeing characteristic X-rays here, and because we are not seeing characteristic X-rays in our observation, where is it? That is, he's doing the signal there. We're not seeing any characteristic X-rays here. And he is not seeing any characteristic X-rays here. That this is the same phenomena. And this is the detonation, in our case, in a sodium iodide, thallium doped scintillator. In his case, a germanium lithium scintillator. He is seeing the same phenomena. No characteristic X-rays, which means the electrons and or photons released from the electron emissions are come from an exotic vacuum object. I believe he's saying the same thing. And that is the definition to me of a maverick. He's seen something and he's putting it out there. And it wasn't until 1996 when Christopher P. Tinsley interviewed Martin Fleischmann in Infinite Energy. And Martin Fleischmann makes a big thing about various scientists. And he mentioned several scientists that observed these unusual X-rays that cannot be coming from even K-shell. They can't be coming from any electron emission from normal things. And it's not a normal nuclear emission either. It's a range of X-rays. Caribou saw them. Other people saw these X-rays. Edmund Storms saw them. He published a paper in 2011 or 12. He's seeing these radiation that's coming out. I believe this is all exotic vacuum objects that are coming out of the nuclei. And Matsumoto was right there in 1989. Genius. Maverick. It gets even more interesting. It gets even more interesting. Because in his next paper, Observation of New Particles Emitted During Cold Fusion. Sorry, I just want to show this one because I want to show you that I actually understand what he's showing here. He's talking about this experiment here, the 800 degrees C. This is the same experiment, So he submitted this on March the 26th, 1990, and it was accepted March 9th, 1990. So March the 26th, we're barely a year after Martin Fleischmann and Stanley Pons, and he's been in this same kind of experiment. And mind you, this was heavy water rather than light water. He observed what he calls these iton decays, possible iton decays. And what is an iton? It's where you have hydrogen, atomic hydrogen, and we're just going to look at the proton in the center of the atomic hydrogen. An electron cluster around that polarizes the proton to such a degree that it separates out into its constituent parts a neutron, a positron, and an electron. And then the existing electron that is part of the atomic hydrogen combines with the positron and the neutrino into an iton. And the iton is represented like this. It is an electron bound by the neutrino. Sorry, this is neutrino. And to the positron. And this produces EV plus, and EV plus is the iton. Okay? And here we have two electrons, two positrons, and this is from two protons from, this is basically a two proton hydrogen molecule being converted into one I2, which is an E that way, E plus that way with two neutrinos. So essentially you have a neutral cluster of structures because the positron and this structure is neutral and it's a new meson. And so he argues this is a meson mediated reaction. I won't go into that too much, but what we can now see, because we have access to beautiful imagery, is what he was actually talking about. And in this case, he's just talking about background stars and I-type tracks. These can be on your X-rays anyway, right? I won't go into that. But when he was talking about these for your I3s and your I4s, producing these cross patterns, I couldn't understand what this black area here and this white area is. And I'm going to explain this for you now so you can read these images. These are the number of things that he found. Okay. So this is what he calls, and we have all the images for this, for all of these different ones that he observed. So he's finding ones that have a particular angle and the angular distribution of the tracks. But anyway, it's a deep study that he's done. This is a triple crossing. So we have a line across here, and a line across here, and one line across here. Now, what happens on a film, and I only know this because I've been able to look at his films. And if you take a piece of this radiographic emulsion and you put the microscope on it, and there is a track, if the track is going through the thickness of the emulsion, when you change the focal depth, if you get the focal depth right on the point of impact of the crack, it'll appear as a spot. And if it's out of the focal plane, it'll appear as a ring. So these that you're seeing on here are not actually tori. They are out of focus spots. It's a visual artifact. But what that tells you is that where you've got these spots here is they are in the focal plane. And then the ones that are rings out here, or rings over here, these are because they're coming out of the focal plane. And it's a little bit more obvious on his last image here. Maybe it's not. Okay, yes. So here you've got this is in the focal plane. This is coming out of the focal plane. So it's coming into rings. Okay. And probably the same here. So I think what he's drawing, when he's drawing these things here, like this, is that's that's it. That is all in the focal plane, and then this is coming. This is in the focal plane. This is coming out of the focal plane. This is coming out of the focal plane. So that's how he represents. So it's a kind of 3D image of the explosion of these structures. Here you can see one that's exploded in 2 directions. Okay, and this is the point of the explosion. So you see black spots coming into a ring, and over here you see black spots coming into rings. Okay, so that is what you would see represented up here. That's the central point is in focus, and then this is out of focus in one direction and out of focus in the other. Absolutely incredible work. Incredible work. So you're able to understand these diagrams and what they mean, and his total genius here. But it's the next presentation where I got really excited. And it's no, maybe it's not this one, but you can see some of the complicated equations we have to do. Maybe it is this one. Maybe it is this one. Let me have a look. Is it this one? No, it might be the previous one. We might have skipped over it. No, maybe it's the next one. I'll get there at the end. 102. Where are we? Oh dear. Somewhere here. Bear with me. What have you done? Oh, right. Okay. It is this one. This is where I want to stop for today. This paper, observation of new particles emitted during cold fusion. Right. So, Lutz Jaitner has said condensed plasmoids, plasmoid being an abbreviation of plasma toroids, derived from the work of firing multiple toroids of plasma at each other by Winston Bostick. And of course, if you condense those, well, condensed for me doesn't say much other than more dense, right? Okay, and that's kind of what they are. But I'm sticking with fractal. So fractal toroidal plasma toroids, or fractal plasma toroids, that's in my view what they are. And in his work, Lutz Jaitner has calculated that the magnetic pressure at the center of these structures, based on normal accepted quantum calculations, results in a pressure that's 5 orders of magnitude more pressure than you get at the center of Sol, our sun. 5 orders of magnitude stronger than what you get at the center of our sun. And so he says that this is the same pressure you get in a pulsar. Okay? This is the pressure you get in a pulsar, and what that means is you're getting a pulsar is a type of neutron star. So when we look at Matsumoto's work here, he's saying that electron clusters cause a proton to separate into neutrons and a positron and a neutrino, and that this forms an iton which forms a mesh around the proton, and the overall structure is neutral, so it can then compress further. Okay? And you end up with these itons. So the net result is electron clusters lead to formation of an overall neutral structure, the neutron and the iton. And you don't need to believe this, because what I'm showing you at the end there, for me, is incredible. Because I've understood something that only a nuclear scientist who really knew his stuff could teach you. The neutron has no Coulomb barrier. This has no Coulomb barrier. Okay? So this is happening in the point of electronuclear collapse. And he has his book here. If I've got it here, somewhere I've got it here. Maybe I haven't got it here. It's not here. It is his... Oh, no, I have it here. Yeah. This was his first book, and this was published in 1990. I think. And he says on the front cover here, he says, discovered on August the 25th, 1990. So, okay, this is after this. This is after what I'm showing you here, this paper that he published in Fusion Technology. In nuclear emulsion during cold fusion. And this is gravity decay. So that is his gravity decay. Okay? That is what he's showing. He discovered in August the 25th, 1990. Anyway, we get down to here, to the bottom here. Okay. Now we can see the emission of itons during the hydrogen catalyzed fusion. Boom! There it is. How many people have... and in the next paper I'll show you, he coined the phrase hydrogen catalyzed fusion, and you'll understand why. You'll understand why he calls it that. But very simply, you can see it here. You've got two deuterons and an electron, and another deuteron comes in, and that is doing the catalysis. He explains in the next paper why. This goes to quadronium, and that plus an iton and a deuteron, and then the quadronium then decays to 4 helium and electron and an antineutrino. Okay, so the fusion products must be modified on the NATO model. When a single iton is emitted, one of the two fused hydrogen nuclei is fermented, is what he says. Connecting equations 5 with equation 6, i.e. after sufficient time, the unstable particles such as quadronium and itons decay, so we obtain the reaction given by equation 3 in reference 1. On the other hand, for double iton, you end up with this, 4 neutrons, equation 7, or quadronium, which will decay and then produce 2 neutrons. Now here comes the money shot, where Kn is the neutron nucleus consisting of K neutrons. The beta decay of 4 hydrogen in equations 5 and 8 could be confused with beta decay of tritium produced by conventional D plus D reactions. It could be confused by beta decay of tritium produced by conventional D plus D reactions. Here, the neutron nuclei can be considered to decay as follows. Are you ready for this? 4 neutrons go to 4H plus E plus antineutrino goes to 4 helium, 2 electrons and 2 antineutrinos. The 2 neutrons cluster goes to an electron and an antineutrino. Or, now bearing in mind, this is long before he concluded this. This is earlier this year. He's saying, or alternatively, by gravity decay, right? 4 neutrons, I'm going to blow this up even more because this is very, very important. 4 neutrons go to a neutrino and an antineutrino pair. 2 neutrons go to a neutrino and an antineutrino pair. Right, I'm going to give you a couple of minutes to ponder on that and think what the significance of what that is. What is the significance of what I have just showed you? What is the significance of what I have just showed you? Give your answers and I'll pull up a couple of slides that I think can demonstrate it. It's already been calculated that a 5 micron or a 1 micron, I can't remember which, but in 2022 at ICCF 19, Lutziatner calculated 5 orders of magnitude more pressure than at the center of our sun. The same pressure as in a neutron star. What happens if you go further? If you go further than that for that size? If you cluster, what happens if you go further? I'll give you a clue. What are the implications of what I've just showed you there? What are the implications of what I've just showed you there? Yes, Martin Ansel, you get the prize. Matter disappears. Matter disappears. All intents and purposes, matter disappears. Why is that important? Can you see something? I'm going to leave you thinking about that for a while. I just want to find a specific image. One of them. A specific image is fine. Matter disappears. What is the significance of that? That'll do for a start. There we go. Paul O'Neill says, where does it go through? It goes through to extremely energetic neutrino and antineutrino. Extremely energetic. But because they don't interact with ordinary matter, they just sod off. They just go away. They disappear. Right? Unless you've got something with a very, very big toroidal moment nearby. They can suck them up. They can suck them up. The energy hasn't disappeared. The matter's disappeared. It's left where it was. It's not there anymore. It's vamoosh. Okay, I've nearly got what I want. Okay, I'm gonna share a couple of things, and then I'm gonna find out what I really want, really want. Yeah. What you are looking at here is an image I took on 17th of August 2023. And this is some of the Hutchison fragments that I received from George Hathaway of the very, very famous sample of the large section of metal that crumbled into these fragments. This is the one that is described as by Tom Bearden in his videos as fragmenting and looking like Venetian blinds. Here's the Venetian blinds splitting across the crystal grain. Okay. And it had all these holes. And these holes are, as Matsumoto observed, on the crystal grain boundaries. Here. Now, these holes are semi-equidistant and they are literally chewing through the material. In this particular structure, you can see that they have a toroidal structure to them. So there might have been another crystal plane on top of here, and the toroid was here, and it was eating away. They're regularly spaced, regularly spaced. Okay. You can see here on this one here, these toroidal type structures chewing away and consuming, but regularly spaced. So sometimes you get the holes, and sometimes you get the toroidal bit. It's a larger area here. Sometimes the toroids are filled with carbon. So we essentially proved the analysis of Hathaway to be correct. The distance between these points is exactly the same and like the triangular section in the cardioid infarction of Henk Urien, which means this is a predictable quantization level of the topological monopoles. Okay. Yeah, look how it's eaten these grain boundaries away. This is quite bizarre. It's almost gone out in the loop and come back. Now, in my view, these monopoles arrange themselves like this probably because of the scalar interferometry producing the monopoles and focusing the energy at a point at which the matter collapses. In this case, it's removing the matter and or leaving carbon deposits there. I'll have another window which we can look at, which is a different data. Maybe I got a comparison here. Yeah. So in this image, on the top left, you have Henk MFMP brass. This is the one that I was talking about. And down here at the exact same scale, you have the Hutchison, my imaging of the Hutchison sample, which is a ferrosilicon material from around about 1980. The same distance between the center of these vortex structures in the brass compared to the ferrosilicon. Again, around about 1980, this is the aluminium sample. I've talked about this recently, which has iron-rich structures in the center of these scallop structures. But in the center of the overall macro, it has copper. So what you're talking about is pressure. You know, you add more pressure to aluminium and you fuse and get iron, but there's a lot of material disappeared in here, I have to say. And over here, you've got a lot of material in the overall structure and a copper structure here. But this isn't the one that, you know, I've shared other ones where John Hutchison had cut a sample in half, and inside that sample, he saw spherical sections cut away. Spherical sections cut away. And this is not too dissimilar to this paper by Matsumoto that was received September the 21st, 1991. So this paper here was received at the Fusion Technology Journal just a couple of weeks after, or a week after, he wrote that first book on gravity decay. And he cut open his palladium electrodes to find that the inside of the electrode had material eaten away and in spherical sections on the boundaries. Okay? Spherical sections on the boundaries that then grew and consumed more of the crystals, like so. And he proposed that it happened like this. These spherical sections start, they grow, they get bigger and bigger. They start consuming the crystal grains and lead to the disappearance of material. Okay. So this is what he found. See a similar thing in Hutchison effect, and we've seen other material, but I think there's one video that does even better at showing this phenomena, and I'm going to get it for you now. And I published this nearly 8 years ago. And it's called The Challenge of Containing the Active Agent, which I didn't know what it was back 8 years ago, in low energy nuclear reactions. But I did know that you can't let it build up too much. You need to bleed it. You have problems with ceramics. You need to use boron nitride or something. Parkhomov found that boron nitride was the only material that he could get that was reliable. And in fact, I actually have some of his boron nitride in this sample pack from him from his first major heat producing reactor, 400 megajoules of excess energy produced. So I think a couple of these from the central core are from boron nitride. So this was the Hutchison, sorry, you're not seeing this, are you? The Hutchison aluminium that got fluidized. But I think we can all agree that probably, if I've got this, oh, have I got it here? Oh, I don't know. Maybe I haven't got it here anymore. Let me just find that. I think you know what I'm after now. Maybe I can find it on YouTube. It's probably on our friend's site, Math Easy Solutions. Yes. This is the video. "7" by 2" by 2" iron bar. "7" by 2" iron bar.
Get it. What the hell? Just pull it out of the test area over there. And put some paper on in the hallway here.
Okay, I'm going to stop that so there's no copyright strikes. When you understand that you're getting magnetic pressure and the pressure is exceeding that inside a neutron star, and if we combine that potential reality with what is being said by Matsumoto here, that the metal in the center of this sample could be going through gravitational collapse. And as I've said, what goes through the center of a fractal toroid is a gravitational beam. And what John Archibald Wheeler said is that if you get a gravitational beam and you link it to another gravitational beam and another gravitational beam, and they link up, they'll form another gravitational beam. And so if you get a cluster of these things, such a case, they would do two things. One, they would produce three things: an incredible magnetic field. Two, a twisting action. And three, they would eventually lead to gravitational collapse. Gravitational collapse. How on earth did Dr. Takaaki Matsumoto know this? How? Okay, I think that's where I'm going to leave it in terms of this particular Maverick. I think we have a full explanation for what happened to this and to similar effects we've seen in other experiments, including even the other end of this material here. Matter absolutely collapses through gravitational decay. It is gravity collapse. What is gravity? And it leads to this would be one hypothesis that is consistent with our understanding and leads to matter. And because it's extremely fast neutrinos, they're relativistic, they have no time hanging around to interact with your body in order to cause any problems for your body. By the time you've thought about them, they're, you know, out the other side of the moon, right? They're not there. Okay. So, does anyone have any questions? Like I say, I can go on about Matsumoto's papers and I'll do other videos. If people want to pitch in on the Kickstarter, you can still order one of the exclusive books. It is a little bit higher priced now, but the cutoff of that will be soon. So I'm going to see if there's any questions. Did the metal bar heat up, Bob? I'm going to ask Yin. Did John ever say this bar heated up?
No, it did not.
Do you want to say that into the microphone?
No.
Hold the microphone up.
Oh, I think the microphone is close enough. No, no heat was involved. No.
No heat was involved. This did not heat. Yeah, it converted to light. Well, in this case, it converted to neutrinos. I don't know whether the weight changed, but certainly its volume changed. We do know, and I showed you, that in some cases you can end up with a hole filled with carbon. Carbon weighs less than iron, even if it's fully filling that hole. We do know that in certain cases it ended up with a heavier element. This happens in our experiment. So you get a piece of copper in that 1980 sample from George Hathaway, that copper sphere. Now, is the copper being extracted from the aluminium and leaving a hole in its place? I don't know. But it looks like a lot of material has disappeared from that scallop section. And there is a copper bit. So some of it's gone into dense material, which is denser than aluminium. I mean, copper is a lot denser than aluminium. But it isn't so dense that it would have absorbed all of that aluminium. So in the process, maybe some energy in the process is used to provide the process itself, and then some of the balance comes out. But if you are converting a lot of the matter into neutrinos and anti-neutrinos, that goes away and you don't see it again. It's not even a gas. Some could be converted into a gas. Sure, you can get heavy gases like argon-40. You know, it likes to produce calcium-40, and so why not some argon-40 in there? Yeah, so we can definitely see, as people are noting, that there is some fuming, and so the fuming could be particulates, and there could be nanoparticulates being taken away, and also there could be, and we know this is the case, some of the EVOs could become neutral, but they still have a lot of matter internally, and they are traveling away, because we know from Matsumoto now and our own work that EVOs were traveling out of a reactor and going into a scintillator and then blowing up. And we know from the work of Shishkin. Shishkin refers to the work of Barkler, who discovered characteristic X-rays. He found this thing called J radiation. He called it J radiation because it was higher energy than any K radiation, but it wasn't a nuclear thing. It was something else. And he spent the rest of his life afterwards. In fact, his Nobel lecture for getting characteristic X-rays, establishing that they are a thing, was talking about J radiation. And J radiation, in my view, and in Alexander Shishkin's view, is charge clusters, exotic vacuum objects, magnetotor-electrical radiation, these energy solitons coming out of the matter. And they can teleport matter. This was observed by Ken Shoulders. Ken Shoulders observed the teleportation of matter. I believe we've observed the shifting of matter. So, for instance, we have a copper tube, we have a ball lightning form, it blows up, it travels, it hits the fused quartz, the structure breaks up, and it left a copper toroid, or a section through a copper toroid that's splattered on there. Those ions were carried from the copper from one place to another and deposited on the fused quartz. So some matter could be teleported. Some matter could be off-gassed, and yet more matter could be synthesized of a heavier element or a transmuted element, or completely desynthesized into what we're seeing here, neutrino and antineutrino. Nanoparticulates, yes. The smoke could act more like spores. I mean, these I mean, effectively they're static electricity, but potentially carrying ions. They could be, there could be little universes in there. Who knows? So I'm starting to understand why Matsumoto feared for his life and was cautious about accepting food from people he didn't really know. Because all the way back down here in his third paper in fusion technology, he's referring to the fact that it can cause gravity collapse, effectively, into non-interacting neutrino and antineutrino pairs. And then his book that came out, so this was published, when was it? May 1990. And his book came out in August 1990, talking about quad neutron gravity collapse, and that is quad neutron gravity collapse. It wasn't until the late 1990s, and discussed this in a letter to the editor of Fusion Technology, that he admitted that his structures were essentially the same as Ken Shoulder's exotic vacuum objects, but that plasmoids did not sufficiently explain how they're bound together. I think maybe we have bridged that complication there. But he said that what is actually going on is it's not just 4 neutrons that's decaying, it's actually clusters of even microns to millimeters wide that are simultaneously transmuting or being affected. And that is what you see in those images from John Hutchison. This is not a small amount of material that is being affected here. This is a large amount of material. And we're seeing that across systems. This is from John Hutchison. This is Henk Urans Vega, and this is John Hutchison. This is in aluminium. This is in ferrosilicon. Okay, ferrosilicon. And of course, this is actually just straight up bar iron, mild bar of iron. Yes, Ian McClelland. Ian McClelland in the chat has mentioned MH370. I've had to come to terms with what potentially the implications are here. I still maintain that if you make a macro cluster and you shift that and you don't over-energize it, you could do the teleportation part rather than the matter collapse part. But it is the same process at different levels of intensity that give you both effects. The complete, and this is why very early on I said, I don't believe there's any concern at certain levels about ICBMs, because they can literally make them disappear in the sky. They can make them disappear in the sky. But you can't reveal that. And either way, you could teleport them into the sun, or you could teleport them in, or you could make them disappear in the sky. Either way, they're not a threat. But you're not going to be able to get people to spend a lot of money with that kind of conversation, are you? Essentially, this work was done, if we are to believe these dates, and I don't see there's any reason not to believe these dates, March 26, 1990, he may have already come to the conclusion that there was gravitational collapse before 1990. And if this is the case, this would explain this. It would explain what you have here. the Pons and Fleischmann, what I call the singularity here, with lovely illustration by Matt Howarth and the story by Rupert Carrot. There we go, Rupert Carrot, where the cold fusion thing bored through the glass, made it disappear, took out the water, went through the table, and took out a chunk of the concrete, leaving particulates floating in the air that did not settle, which means they have to be below a certain size. Tammy, just go to the Kickstarter, look for it, but I think that at the Japanese conference there will be the family there. I'm still hoping that I have every image and I don't have to rely, because they're going to give me the rest of the materials that I didn't have the extra baggage allowance to take away. There's a couple of holes in the book, and I need to go through the materials I already have to see if I can solve those. But I'm saying that I'm already, I wouldn't say proud because I don't want to display that emotion. But this is going to be a special piece of work, and I think I want to do this guy justice. You know, this guy did some legendary work. And when you read through it, it really starts to make sense, because I'm actually having to read every single comma, every single part of an equation, and try and understand it to make sure that everything is right. And I know Philip Power in New Zealand has done very, very good work on that as well. And like I say, I don't necessarily agree with the NATO model. Well, the NATO model is about encasing it in something that looks like NATO. And when you actually look at this, and you look at NATO beams and the webs that the NATO beam forms, then you can really think that he's not far off. You can think the same thing with this. You can think the same thing with this. So I can see where he comes from, and I've actually got these pictures. And Sho, who was with me in Japan, he went out and got the beans and the fermented, and he showed you how you make it as a food, and it actually goes all sticky, and it looks like this. It looks like this John Hutchison sample. It really does look like this, the beans. So I don't think he was too far wrong in terms of the word to describe it, and it's kind of weird. He might be on the money, but it doesn't explain some of the things that he's seen, his toroidal geometry, and I wonder whether there was some confirmation bias going on when he chose particular images out of that image set which showed these toroidal structures, but he didn't choose the ones that showed the fractal toroidal, which I shared in my Strasbourg presentation. And these images in his photo sets were in between his black hole images and the ones that he actually chose. You know, they're in the same series of images of radiographic plates. So, you know, sometimes when you have an idea, you want it to be that. But in terms of what he's sharing here, you know, he nailed it right on the money with his first intuition that we're going to have to rethink the way the Earth was made. He nailed it. He was there. Like, this is 1989. It took us till February 2016 to see this, right? So far ahead. Whatever's going on in here, it's not normal radiation, because he's an expert in normal radiation, although he does say, because of cosmic rays, you do get some of these structures forming. But there is literally no one with the competency that I'm aware of, and I have asked in the Lena field, that would be able to read any type of radiographic emulsion. It's so sad, really. And the fact that this allows him to understand this, that ultimately you get down to gravity decay. And when you know that that is a possibility, assuming it is, then when you combine that with the understanding of one of the leaders of the Manhattan Project, John Archibald Wheeler, and the fact that he says gravitational waves linking together can cause a collapse down to a black hole, and Matsumoto shows the pictures of the black holes, then I don't know what conclusion you can draw other than it is this intense magnetic pressure that leads to exactly what was observed in the work of John Hutchison and in our own work, that if you push it too hard, it can cause gravity collapse. It can cause gravity collapse. I'm very glad that John Hutchison is alive to see this. I'm very glad that John Hutchison is alive to see this. Thank you. If this is the case that this is gravity collapse, then you all should understand that this also gives us a tool for gravitational vectors. When you have gravitational vectors, or rather you are able to project a neutrino beam, then you have propulsion as well. Okay, I'm going to look to see if you've got any question. Right, Ian McCallum says, set up a bigger cursor. All right, I will try to do that. Yes. So, Scott C., what was that comic book of Ken Shoulders? That wasn't a comic book of Ken Shoulders. That was a comic book of Pons and Fleischmann. So you've got a sketch of Pons and Fleischmann there. Fleischmann, Pons. Okay. And you've got the story of the shenanigans going along with Stephen E. Jones and stuff in here. And it's funny because, again, you know, in the Matsumoto archives, he has 2 or 3 large volumes of the first 2 years of muon catalyzed fusion research. And these were people all over the world going to international conferences, right, on muon catalyzed fusion. And so right at the point where muon catalyzed fusion was really getting its grounding, you had this competing theory coming out, which could result in actually producing fusion, because people knew that whilst muon catalyzed fusion worked, the muons, that they take too much energy to make or that's the story you're told, to actually be productive. But if you go and look at these first papers, you know, this is number 1 that he published, and down here we look, Martin Fleischmann, Stephen E. Jones. And we go to number 2. Where we go? Martin Fleischmann, Stephen E. Jones, right? This is where it's at. And when you start to go to his later publications, he's referring to T. Matsumoto, T. Matsumoto, T. Matsumoto. Fleischmann, Matsumoto. He went past Stephen E. Jones and Matsumoto very quickly. Here's the next paper. Martin Fleischmann, Stephen E. Jones, Matsumoto. Some of his colleagues, very important work they did. C.M. Lederer, okay, and this is just a table of isotopes, and Matsumoto. So he had no one else to refer to. There was no one else that was working as hard as him and as innovatively as him right at the beginning. And my God, did he nail it. Matter collapsing from within a structure, being consumed. But this is cold fusion, and the structures forming because of electrostatic pressure in the optimum places in the crystal grain structure. What John Hutchison is doing is using electromagnetic waves to produce these structures in particular places in the lattice. And if you focused it right in one particular place, making a very large phase conjugated node, then you are ending up with very, very large structures, basically making the matter disappear. Either in this case, you know, collapsing it into heavier iron or even heavier copper, or in this case, you know, collapsing it in a regular array. Okay, So this is where it is appropriate. The crystal, and we've actually replicated this in Vega experiments, the crystal grain boundary stuff. But this is using electromagnetic interference of scalar interferometry to produce the effect. Alex is offering his creative services. Yes, that may well be the need to happen. Jack trading, well, not all heroes wear capes. I couldn't agree more. Although I think John Hutchison has worn a few capes in his time, right? Yin?
Yes.
Back me up here. Oh. Gravity, decay, or matter. Oh, right. Thank you very much, Eric Loseman. So he said, I made comics for Eric Dollard and Eric Lerner. Yeah, certainly we need to make this child's play. And I mean, the Ultra experiment is child's play. Matsumoto's simple experiment that he preferred is child's play. But this, if this works, and we're going to find out soon, because we're going to do a lot of these experiments. If this works and shows the magnetic collapse. So whilst this process may not be synthesizing other elements other than iron, or it may just be aggregating iron, my point about this is this could be your starter, your introductory experiment for the skeptics that's even more cheap, like $4, and you can do hundreds and hundreds of experiments, right? $4, hundreds of experiments. There's zero barrier to entry. And that's only if you're paying for the bits. If you go and take these out of old electric components and nix some kitchen foil and distill your own water and then oxygenate it, then it could essentially be free. All you need is to find some old batteries at your dump, because they don't need to be high current. They just need to be the right voltage to charge this up. And then you're good to go. So, you know, if it is extracting the iron fragments from the aluminium and compressing that into an iron-rich crenellated hollow sphere, then that's going to mess with a lot of physicists' brain. It's a magnetic pressure. Tammy, that's okay. But at some point, you will have all you need to know. And you will be able to demonstrate these things in front of him. It'll still look like a magic trick. I think John once said if we take a low loader and we demonstrate all of the effects around New York, no one would actually believe it when they saw it in front of their eyes. Right, Yin?
Absolutely.
You say, what do you want to do? Make this metal crush and twist? And they would say, oh, you've used a piece of rubber. It'd be like, oh. I had this last night when I was on Thursday when I was speaking to these researchers. Like, I mentioned neutrinos, and then they start rattling off what they've last read on Wikipedia about neutrinos, and I go, no, please. And then I managed to get to that person to the point of moving forward from what he thinks debunks anything I'm about to say next. And we waste 20 minutes on that. And another person sits down and starts the same process again. And I say, look, I've been through this part of the conversation. Check in with him later about what I said. I want to move on to the next part of the conversation. Claire Westwood, where can we find... So from the Ultra experiment, go and look up Ultra, ULTR, on the Martin Fleischmann Memorial Project's YouTube channel. I will be doing, you can go and look at, search for Tibby. I'm going to be referring to all of these experiments as Tibby. But I will try and replicate this in the coming weeks and hopefully get it under EDS and SCM and do a deep dive. I hope to be able to get some very high fidelity, close-up macro, high-speed videography of the process going on. And if we find the iron-rich crenellated spheres and or more, then you will know, and I will do a end-to-end. But basically, Tibby's already done that. It's such a simple experiment. Okay, so I think I'm going to leave it there. If no one's got any burning desire to have an answer for something very quickly, I'll give you a small window now. Because I have to do something in the morning tomorrow, and so Yin's joining me. So hi Phil, great to have you here. I hope you enjoyed our videos. Oh, Yin's got something. Yin wants to say something. Ask something?
Yes, absolutely. As DIV projects already put in the chat earlier, we have another Maverick among us. His name is Maverick Bob.
Oh, come on.
Thank you for your work.
Oh, well, thank you, Yin, for reinforcing. That's very kind. All right, Nathaniel. Thank you very much, Mark, Dan, for that $30. That really helps. So, Scott C., you missed the fact that John is out of hospital. He's not had the stone in his bladder removed. I think he's in recovery phase before they attempt that. 3 is saying, Bob, what do you make of the new info regarding the newly found shafts? I commented in that recently. You go and look at last week's presentation. I commented in that, and already the people that I'm working with, one in Canada is measuring trying to work out the distance that the etheric matter rays travel. And my colleague Paul, also in Canada, is going to, we actually have actual quarry stone from the Aswan quarry of the marble and of the granite. So we're going to be able to make, say, 5 or 10 meters of actual Aswan limestone and actual Egyptian mined granite, and we're going to be able to put those in and see if we can x-ray through that. So I will publish a video probably tomorrow or maybe Tuesday of us discussing our plans for that. I think I recorded that. Anyway, that is underway, but I'm going to focus, if we can do this, on imaging the Great Pyramid and try and get permission for that once we've demonstrated that the process works. And if that's so, we can non-destructively understand the inside of the Great Pyramids, and then we can use the same process on the Khafra Pyramid to find out whether any of their data actually makes sense from a different imaging technique. Okay. All right, so yeah. This has been Maverick. And go and have a look at Pavel Asmira, his water treatment system. I think he's done a wonderful job. I've got another video of his to share, and also I will link the paper that I showed earlier on and link to his website, so you can see his fractal vortex ring theory of matter, and the fact that in 2009 he predicted a wheel within 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 a wheel, at least on his first drawing. So he's definitely getting into the vibe of the fractal structure of how an electron is formed. And here was me at the final meeting of one of the European funded projects, being embarrassingly apologized to for a couple of hours, but thank you. And I look forward to working with them moving forward. I'm quite excited with that. and I think we can do some great things together. So I gave him all of the equipment, the difficult to find equipment. I mean, this took me, well, I had to go to the electrical shop, and that I had to wait in the queue for 12 minutes. And then I had to go to the pharmacy to get the distilled water, and that took me another 6 or 7 minutes. So I could have already done an ultra experiment at home in the time that I wasted getting the equipment together to do this experiment. But I battled through, and I managed to get the important equipment. So I didn't have 5 years to waste, but or 6 million euros, but I did have $3, and so I spent them in the way that I saw fit to give him a gift, so that we could move forward. And I hope that he takes that to heart, and we can do some wonderful science together. So if Yin would like to say goodbye.
Goodbye to you all. Till next time.
Round like a circle in a spiral, like a wheel within a wheel, never ending or beginning on an ever spinning reel. Like a snowball down a mountain or a carousel balloon, the world is like an apple running rings around the moon. See you later.